Hi, in this lesson or set of lessons, we're going to learn why we get very good at drawing hexagons in this class. But first, I'd like you to meet Belle. She tends to bark whenever I talk to the camera. So if you ever hear barking, you'll know it's her that's doing it. I'm going to let her go because she's not very comfortable right now. So as I said, we get good at drawing hexagons. We drew cyclohexanes before, and now we're going to draw benzene rings. All of these are very important. That's why there's a hexagon in my logo. So from our lesson on alkenes, we know that if you take cyclohexene and treat it with bromine, you will have a trans addition across the double bond, and this happens at room temperature. It is an easy reaction. It's been used historically to test for the presence of alkenes because alkenes decolorize bromine. If I take this structure right here, which is, if you think about it, we would call it 1,3,5-cyclohexatriene. If these were all alkenes and treated with bromine, you would add across all of them. But if I did this, I would get no reaction. So there's something different about these double bonds. If I take cyclohexatriene, but now we're going to call it benzene, and I treat it with bromine with a Lewis acid catalyst, FeBr3. It's actually fairly easy to make this. All you do is add Fe plus Br2, and the Br2 will oxidize the Fe to FeBr3. So you just throw in some iron filings, heat it up, you're going to get a different kind of product. Instead of an addition reaction where the double bond goes away, we get a substitution reaction where one of the bromines substitutes for one of the H's, and you'll get HBr as another product. So why does this happen? This is because these double bonds are not alkenes anymore. They're aromatic double bonds, which is a completely different kind of stability. So this is a different functional group than the alkene. So we're going to talk through this diagram right here to try to understand what it means and why it proves that there's something different about these double bonds. Now, what we're looking at here is the energy released when you take an alkene and treat it with H2 and a catalyst. Platinum, palladium, anything will work with this alkene. And what we're looking at is how much energy or heat is released as the alkene, cyclohexene, goes down to cyclohexane. Now, if you only have one double bond, you lose or give off negative 118 kilojoules of heat. Now, if you have two double bonds, this is what's called conjugated. If you have a double, single, double, anywhere in your structure, these double bonds are called conjugated. It means that the orbitals, the pi orbitals, sort of talk to each other and stabilize each other. So instead of completely doubled the amount of heat, it's a little more stable when you have conjugated double bonds. So as you reduce this with your H2 and palladium down to cyclohexane, you're going to lose or give off 230 kilojoules of heat. So if you think about it, the next one would have a little more conjugation. If this were truly cyclohexatriene, you'd expect it to give off maybe a little bit less than another negative 118. So I'm putting parentheses or quotes negative 350 kilojoules. But lo and behold, when you take benzene, we're not going to call it cyclohexatriene. We're going to call it what it is. And you actually can't use palladium or nickel. You just have to crank on it with a high pressure of hydrogen and platinum in order to reduce those double bonds all the way down to cyclohexane. And this gives off only 206 kilojoules. So instead of being way up here, we have an extra 150 kilojoules of stability because these double bonds are arranged in a planar ring. So the reason why benzene or compounds like it have extra stability is because of the molecular orbitals of the pi system. And all of the molecular orbitals of the pi system, 2, 4, 6, there are 6 pi electrons, are in what we call bonding molecular orbitals instead of anti-bonding molecular orbitals. And we're not going to go into any detail with this, but in order to be aromatic, there are certain conditions that need to be met. The first one, it needs to be cyclic in a circle, and it needs to be planar. Because if the molecule is not planar, the molecular orbitals can't overlap and can't, what I call, talk to each other. The pi system, or the pi electrons, must be conjugated, which means they need to alternate single, double, single, double, single. In addition to conjugated, they need to be able to resonate. You need to be able to draw resonance structures all around the ring. And the third thing, they need to have the correct number of pi electrons. This is called the Huckel rule. And the correct number of pi electrons are generated by this number generator. It doesn't mean anything for n plus 2 other than they need to be even number of pi electrons that are every other multiple of 2. So in other words, 2 electrons, 6 electrons, 10 electrons, those are the numbers that will give you aromatic hydrocarbons. So obviously benzene fits the bill on all 3 of these accounts: 6 electrons, conjugated, cyclic, and planar. There are other compounds that are also aromatic, and we're going to go through some examples right now. It's sort of tricky to draw a 7-membered ring, but I'll do this. Bear with me. And I'm going to put double bonds here, and I will put a plus charge here. This is called tropylium ion. This is aromatic. Now, if we can draw resonance structures with this double bonds moving all over. So here goes there, and there goes here, and then this goes there. So when I redraw this structure, and bear with me, I'm not very good with my 7-membered rings. I'm much better with 6-membered rings. My double bond went here and here and here, and the plus charge moved to this carbon here. So this would be aromatic. It's cyclic, planar, conjugated, it has resonance, and it has 6 pi electrons. If I had this species and I didn't, oh, that one's much better. And I didn't have a plus charge. In fact, I had 2 H's right here. Even though you'd say it's cyclic, planar, conjugated, and the right number of electrons, it can't do resonance because if I move this double bond here, the hydrogens would block it and you can't have 5 bonds around carbon. So this structure right here, now I'm going to put a hydrogen, and now I'm going to put a minus charge right there. Remember, a minus charge on a carbon means 2 electrons. So there is an electron pair on this carbon. We're going to count that as a set of pi electrons. 2, 4, 6. This is cyclopentadienyl anion, and this is definitely aromatic. It's very important in organometallic chemistry. And you would not believe that you can put a double bond in a teeny little cyclopropane and then have a plus charge here and have this stable. But this cation is stable because of aromaticity. So let's look at a couple compounds that aren't aromatic. If I have 1,3-cyclobutadiene, this structure is so unstable you can't even isolate it very easily. It acts like a radical. And we'll learn about radicals in a little bit. A radical means that you have two unpaired electrons. So even though it looks like everything is all paired, it acts like a radicals and it's very unstable. In fact, compounds that have the other even number of pi electrons are either anti-aromatic or non-aromatic. If I take a stop sign, and I'm going to draw my stop sign here, and put double bonds here. What happens with this has 8 pi electrons. And it's cyclic, it's conjugated, you can have resonance. It doesn't follow the Huckel rule, but what happens is this is not incredibly unstable. This folds so it goes out of the plane. So it's non-planar. And so this is non-aromatic. Whereas this one can't get out of the plane. So this is actually what we call anti-aromatic.